Hello learners and welcome to practice exam number 4. So exam number 4 is going to be focused on chapter 17 and 21. It will be approximately 12 questions and you will be given about 1.5 hours. All right, folks, so the practice and approach are always going to be the same for exam number 4, and for the final, you are not allowed any note cards, and during the exam, you will not be helped with any question. So you want to make sure that you are completing all the lectures and the homework. Make sure you have a strategy/approach for each question. Make sure, of course, that you practice, and you review what you do, okay? And one of the main things I want to make sure you focus on as well is the actual formula sheet that is given to you. These are all the equations given, and they're very useful for the overall exam. A lot of times, some people ask questions that are literally right here in front of you. So make sure you are using this to your advantage. Now, because there are no cards or anything like that, you want to make sure that you study and practice. A lot of times when folks do not have note cards or extra help, sometimes they resort to cheating. Remember, you do not want the consequences of cheating. It is not worth your entire future. All right, and just to reiterate, please use your formula sheet to your advantage. Use your formula sheet to your advantage when you get on the final exam as well. It's always going to be helpful to you. Let's go ahead and get started. Question number 1 states, balance the following redox reaction if it occurs in basic solution. What are the coefficients in front of Cl2 and OH minus in the balance reaction? So a lot of things going on. First, you are balancing the redox reaction. For us, when we were learning about chapter 17 material, of course, we learned about balancing our redox reactions with the half reaction method. So you want to make sure that you are writing down notes about the half reaction method. Next, they're telling you that there are going to be coefficients in front of Cl2 and OH minus. They give you this overall reaction here. And we'll go through the half reaction method to basically go through the process, right? But as you can see, there is no OH minus. So the fact that they're already telling you, hey, there's going to be an OH minus, that should already say, oh, well, if I follow the overall directions of the entire process, then I definitely should see OH minus in my overall reaction. Let's go ahead and write some notes down on the side. All right, so for the half reaction, you want to set up half reactions, but you also can use oxidation numbers to help you get through. So with the half reaction method, sometimes you have to wait all the way until you balance charge to figure out if something's going to be oxidized or reduced. And that can cause a lot of confusion for folks. But that doesn't mean you can't just automatically use oxidation numbers up front if it is easier for you. Next, you want to balance atoms, and then atoms that are not oxygen and hydrogen, and then you want to balance oxygen and hydrogen. Next, you want to balance charge. Then you want to combine the half reactions and cancel any species that are the same on both sides. And then finally, you want to double check. So for our overall reaction here, we have Cl2 gas is going to decompose into ClO3 minus and Cl minus. And they want us to balance this in basic solution. So this entire setup is going to be for acidic solution. We need to make sure that we add a step here for basic solution. So there's going to be another step added here, and that after we actually get our combined overall reaction, we need to neutralize H plus by adding OH minus. And so that's how I think of it. I write all the steps I can remember, and then I remember, okay, for basic, I have to add in one little step here. Now, don't be alarmed by this reaction here. This is going to be your disproportionation redox reaction, and that just means that you have a reactant here that is going to simultaneously be oxidized and reduced. So when you write your half reaction, Cl2 is going to be the reactants for both of them. So that's just basically what that means. And we've kind of seen this before. I believe it was like chapter 14 or something, so you just got to go back and remember those tiny, tiny little details. But again, don't be alarmed. Just go ahead and let's set up our half reactions here. All right, here we are. We have our Cl2 is forming ClO3 minus, and then we have our Cl2 is forming Cl minus, okay? Now, automatically, like I said, you can set up your half reactions, what we're doing, and use oxidation numbers. Like, for example, we know the oxidation numbers here are going to be 0 and 0, and this is going to be -1 here. So we know that this definitely is going to be a gain of an electron, and so this definitely is going to be reduction. So if we know this is reduction, this automatically is going to be oxidation. And that just makes the rest of our process go a little bit faster. So now what we need to do is balance atoms, and then we're going to balance anything that basically is not oxygen and hydrogen. So of course we have our chlorines here, and we have 2 here and 1 here, so we need to put a 2 in front of here to balance our chlorines. Same thing here, we have 2 and only 1 here, so we need to put a 2 in front. Next, we're going to balance oxygen first. So here there is no oxygen to balance. Here we do have 6 oxygens, so 2 times 3. So we need to balance oxygen by adding 6 water molecules. All right, so if we're adding 6 water molecules, let me write this up here as oxidation, and then this one for reduction. Okay, get all this stuff out the way. All right, now I have oxidation here and reduction here off to the side, so it's not messing anything up. So we have balancing our oxygens here. Everything's great. There's nothing to balance here. Now we need to balance our hydrogens. So we have 12 hydrogens. That means we need to add 12 H plus to this side. All right, now we need to make sure we balance our charge. Now we know this is reduction, so there should be a gain of electrons here. Let's go ahead and figure out how many. So here we have a charge of 0 on this side, and we have 2 negative charges here. And so in order to make this entire side also negative, we need to add 2 electrons to this side. So now we have 2 negative charges, and this is going to verify that again that we're gaining electrons on this side. Now here, let's see how many charges we have. We have 0 on this side, and then we have 2 negative charges, and then we have 12 positive charges. And so altogether, we're going to have 10 positive charges here. Now, again, we are losing electrons here, so we want to make sure that we get 0 on this side. That means we need to add 10 electrons on this side in order to balance everything out. So I'm going to add 10 electrons here. So let's go ahead and rewrite both of our half reactions. All right, so we have our half reactions here. And now, of course, what we're going to do is combine and cancel things that are the same on both sides. But before we do that, we have to finish balancing our charge. How do we do that? We have to make sure we have the same amount of electrons on for both of our half reactions. So we have 10 electrons here, and we have 2 here. So we need to make sure we multiply this entire half reaction by 5. If we do that, that's going to change all of our coefficients here. So this will be 10 now. There'll be a 5 here, and then, of course, there'll be 10 electrons here. All right, so now we are good. Both of our half reactions are balanced, and the charges are balanced. Now we can both go ahead and combine and cancel. We're going to be canceling our 10 electrons on both sides and bringing everything else down. So we have 6 H2O here. We have 5 Cl2 here and 1 here, so that's going to be 6 Cl2. All right, so we have all those for our reactants. Now we have 10 Cl minus here, plus 2 ClO3 minus, plus 12 H plus. All right, now we've kind of went through all these 4 steps, but we are in basic solution, so we have to make sure we neutralize this H plus here. How do we do that? Well, if we have 12 H pluses, we need to make sure that we add 12 OH minus. And if we do that, we're going to form 12 waters here. Now, if we add 12 OH minus to this side, we have to add 12 OH minus to this side as well. Now, the final thing is going to be continually canceling things that are the same on both sides. So if we're looking here, we're like, okay, we have 6 waters on this side and 12 on this side. So we can get rid of these 6 here, and we'll have 6 left. And then that's pretty much it. We have our OH minus over here, our Cl2, everything's the same. So now we can make a brand new overall reaction, and then we'll go from there. All right, so here is the overall reaction that I have. I have 12 OH minus aqueous plus 6 Cl2 gas. It's going to form 10 Cl minus aqueous plus 2 ClO3 minus aqueous plus 6 H2O liquid. As you can see, I all have all the states of matter. Everything looks good. But remember, we want to make sure that we have coefficients that are the smallest possible number that we can have. And so as you can see, we can actually divide this entire reaction by 2 to get smaller numbers. I can divide by 2 here and get 3. Divide by 2 here and I'll just simply get 1. Divide by 2 here and I'll get 5. Divide by 2 here and I'll get 3. Divide by 2 here and I'll get 6. So the reduced form of this overall balanced reaction will be the correct answer. So let's go ahead and write this overall reaction again in the correct reduced form since we have to divide by 2. You always want to look at the final balanced reaction and see, hey, can I get it into lower numbers? This time around we could, so let's go ahead and write that. All right, so then our official balanced equation in basic solution is 6 OH minus aqueous plus 3 Cl2 gas is going to give 5 Cl minus aqueous plus ClO3 minus aqueous plus 3 H2O liquid. Now let's go ahead and answer the question. What are the coefficients in front of Cl2 and OH minus? So there is a 6 in front of OH minus and there is a 3 in front of Cl2. So our Cl2 coefficient is going to be 3 and our OH minus coefficient is going to be 6, and that will be the final answer. For question number 2, it says, use the tabulated half cell potentials, which are given here, to calculate the equilibrium constant for the following balanced redox reaction. So you have 2 aluminum solid plus 3 Mg2 plus aqueous is going to give 2 Al3 plus aqueous plus 3 Mg solid. So for this question, you are trying to relate our equilibrium constant to our standard cell potential. And so, of course, there is going to be a formula that's given to you that relates these automatically, and that is E naught of the cell is equal to 0.0592 volts divided by N log of K. And so that should get you the correct answer. Also, automatically, I'll tell you that there is a tiny little mistake here. This should be a 3, not a 2. Okay? Just keep that in mind. Now, if you're trying to solve for K, which is what they want, you could say that log of K is also equal to N E naught divided by 0.0592 volts. Again, these are both given to you, so you just need to know how to utilize and manipulate this. Another thing is to go further and say, okay, then K, since we have to take the log of both sides, is going to be 10 raised to a power of N E naught divided by 0.0592. So whatever your calculator allows, you know my calculator is going to allow these two, not this one here. So just whatever you allow. And remember, this is raised to a power of N times E naught divided by 0.0592. Okay, so if we know we have to use this overall equation here in order to solve for K, then we need to make sure that we're getting all the other pieces. So we do not have E naught of the cell, we have to find that. And then we do not have the number of electrons that are transferred, we have to find that. So what is E naught of the cell? E naught of the cell is going to equal to E naught of the cathode minus E naught of the anode. So we need to figure out which one's the cathode and anode here. A fast way to do it, again, you can sit here and say, okay, I'm going to balance everything, et cetera, et cetera. You can look at, of course, the standard cell potential values, or you can just look at oxidation numbers. But for this particular type of question, it's easier to understand it through oxidation numbers. Again, these are simple oxidation numbers that are already given, so you don't have to do much to figure out which one is oxidized and reduced. For example, you're going from 0 here to 3 plus. That's a loss of electron. Automatically, you know this is oxidation. If this is oxidation, then this overall reaction has to be reversed. So I go ahead and I reverse that. And I have 3 electrons. Next, you know that this then is going to be reduction here. And so we can leave the overall reaction the way it is. Next, we're going to figure out what our number of electrons are. We have 2 electrons here and 3 here. So we need to multiply this overall reaction by 3 and multiply this overall reaction by 2. Let's go ahead and rewrite this. All right, so we have 3 Mg2 plus 6 electrons is going to form 3 Mg solid. Then we have 2 aluminum solid is going to form 2 aluminum 3 plus 6 electrons. So again, we can get rid of our 6 electrons, and we're left with the overall of 2 aluminum solid plus 3 Mg2 plus is going to form 2 aluminum 3 plus 3 Mg solid. All right, now we can go ahead and get our E naught because we already know which one is the anode, which is oxidized, and whichever one is reduced is going to be the cathode. So we can say we have our negative 2.38 volts minus our negative 1.66 volts here. This entire thing is equal to negative 0.72 volt. So now we can say, okay, I have my E of the cell value. The number of electrons that are transferred is going to be 6. I have both of these values. Now it's time to plug and chug into our overall expression here. All right, since I have all of my values, I'm going to use my log of K expression. Again, these are both given. So log of K is going to be my number of electrons transferred, which is 6, multiplied by my standard cell potential here. That is going to be negative 0.72 multiplied by 6, and that is equal to negative 4.32. I'm going to divide that by 0.0592, and I get negative 72.97297. I'm going to take that negative 72.97, and I'm going to raise 10 to the power of that number. So I have 10 raised to a power of negative 72.97297. When I put this into my calculator, I get K is equal to 1.1 times 10 to the negative 73. Now, normally, based on what's given, you would have 3 significant figures. But from the question, they only give you 2. So I'm going off of what they give me. Instead of the 1.06 that I actually had, I now have 1.1 times 10 to the negative 73, which will be letter C. Now, again, you will see why I made a mistake and actually wrote a 2 here, and it should have been a 3, which is going to, again, match our answer. All right, number 3 says determine the cell notation. So we got to figure out what cell notation is for the redox reaction given below. Circle your answer. So cell notation means that you're going to take your anode, you're going to form a salt bridge, and then you're going to be writing your cathode. It's a way to summarize what the voltaic cell components are in a quicker notation form. So you definitely are going to have your anode and cathode first, and then you need to have each phase change have a single line between them. And then you also need to have inactive electrodes if there isn't any solid present for the overall ions to, or for the redox reaction to be able to plate out onto. So how would you go about doing this? Well, first you need to figure out which one is oxidized or reduced. You can get that from half reactions or simply from oxidation numbers if it's quick. With these type of questions, it's easier to get it from oxidation numbers because we simply have 0 here, -1 here, and 3 plus here, straight from the charges that are given. So it makes it way easier to figure out, okay, wait a minute, this had to have gained an electron and this had to have lost an electron. Automatically, that is going to be our oxidation and our reduction or our half reactions that we can set up. Next, you're going to then use those half reactions to set up your overall notation, which is what the question wants. And then you must make sure that you verify everything. You must make sure that you have a solid, and of course, an aqueous form as well. And also, if you have the same phase, you need to make sure you have a comma in between them. And then also, if you have the same phase and you don't have anything solid for it to plate out onto, you must make sure you remember the inactive electrode. So there's 2 types of inactive electrodes. There's going to be platinum or graphite. Most of the time we choose platinum because it's not really reactive. Graphite isn't as reactive as well, but platinum is the least reactive. So most of the time you see platinum as the electrode that you can use. But if you put graphite, it won't be wrong, right? So you want to use those inactive electrodes if needed. Well, let's go ahead and set this up. First things first, we already know which one is oxidized and reduced. So let's set up our half reaction. All right, so we have both of our half reactions here. We know that this 3Br2 gas going to 6Br minus aqueous is going to be reduced. So therefore, it is at the cathode. You always remember red cat if you like. And then, of course, if this is reduced at the cathode, then this must be the anode and, of course, oxidized, which is going to be 2 Fe solid going to 2 Fe3 plus. So if this is oxidized, it's giving its electrons to this Br2 gas to form 6Br minus. But this Br minus have nowhere to go, meaning there is no solid for it to plate out onto. So you have to think about an inactive electrode here. And I'm already thinking about that just from the half reaction. All right, let's go ahead and fill out our notation. So we have to write the anode on the left, and this is going to be here. So we have our Fe solid. We have a phase change, so we have to have a line. And then we're going to have Fe3 plus aqueous. All right, so that sums up our anode. Now we have our salt bridge. And next, we're going to have our Br2 gas, okay, phase change, Br minus, and that is aqueous. Now, we already know that we need something solid for this overall process to be complete, and we already talked about how we need an inactive electrode here, so I'm simply going to add platinum. Now, platinum is a different, it is a solid, right, so you need to make sure you have a phase change line for this. So that is the cell notation for this overall reaction that's given. All right, number 4 says calculate the cell potential. Now, it doesn't say standard, so that means you automatically are thinking of non-standard cell potential for the following reaction that takes place in an electrochemical cell at 25 degrees Celsius. So they give you the overall cell notation here. So we know we're going to have 10 solid forming 10 2 plus ions, and it's going to be in 1.8 molar concentration. You have a salt bridge, and so this has to be the cathode here. I can automatically start writing details like, okay, this is the anode, just from cell notation. This must be the cathode, meaning this is reduction and this is oxidation. And I can go down and look at this for my half reactions as well and say, okay, this is going to be reduction here and this is oxidation. Automatically, I can reverse this overall reaction because I know it is oxidation. All right, now for the cathode part, we have Ag plus and the concentration is 0.055 molar. And then, of course, we have Ag solid. So there's nothing else to add. We have our half reactions. We can go ahead and take our half reactions to get an overall reaction. Now, why are we doing this? Because we are trying to look for non-standard cell potential, and there is a given equation, which is going to be the Nernst equation. Non-standard cell potential is equal to standard cell potential minus 0.0592 divided by the number of electrons transferred, log of Q, okay? And then we have standard cell potential is equal to the standard cell potential of the cathode minus the standard cell potential of the anode. We also know that Q is going to be equal to the concentration of the products divided by the concentration of the reactants. And we can get that from a balanced chemical reaction. So we need to make sure that we are getting all the pieces to this Nernst equation. So our N value we can get from our half reaction. We can get our E naught value from our half reactions. We can get our Q value from the overall. So let's do that. So first we have our redox, we have our oxidized portion. We need to make sure that they are balanced as far as the electrons as well. So we have 2 here, we only have 1 here. We need to multiply this whole thing by 2. Let's go ahead and get the overall reaction. That's going to be 2Ag plus now, plus 2 electrons here is going to give 2Ag solid. And then here we have a 10 solid. It's going to give Sn2 plus, which we know is aqueous, plus 2 electrons. We can get rid of our electrons on either side, and so our overall reaction is going to be, all right, so once I get rid of my electrons, our overall reaction is 2Ag plus, again, plus 10 solid is going to give 10, 2 plus 2Ag solid. Now my Q overall is going to be my product divided by my reactant. We do not use our solids here, so it's going to be the concentration of Sn2 plus divided by the concentration of Ag plus squared, because we have a 2 in front of it. That's going to be 1.8, which I get straight from my overall cell notation, divided by 0.0555 or 0.055 molar squared, which again, I get the concentration straight from my notation. That means that's going to be 1.8 divided by 0.003025. When I take these two numbers and divide them, I get 595.0413223. And so that is my Q value. Now, since I know I have to take the log of Q, I go ahead and get that number. So log of Q is log of this number here, which is equal to 2.774547126. And so that's the value I get for log of Q. Now, since I know I have to multiply log of Q by this number, 0.0592 divided by N, I'm going to take my 0.0592 divided by the number of electrons transferred, which is going to be 2 electrons here, and I get 0.0296. Now, since I know I have to multiply this number by my log of Q, why not do it right now? So I'm going to take my 0.0296 and multiply by my 2.774547126 value, and I get 0.082126595. So I have both these values here, okay? Now I need to get my standard cell potential, and that's going to be my cathode minus my anode. My cathode is 0.80 volts minus my anode, which is negative 0.14 volts, and that's going to give me a positive 0.94 volts. Now that I have my standard cell potential here, I can take this value and subtract it by this value, and I'll get my non-standard cell potential and therefore the answer. Let's go ahead and do that. All right, so I'm going to take my standard cell potential, 0.94 volts, and subtract it by my value here, which is 0.082126595 volts, and I get plus 0.86 volts, which is letter E. All right, so number 5 says, what mass of silver can be plated onto an object in 67 minutes at 8.70 amperes of current? So they're asking us what mass of silver can be plated onto an object. And so they're talking about a non-spontaneous reaction, okay, especially since you have to add a current to it. We're thinking of an electrolytic cell. And so when we're connecting that information, we're thinking of Faraday's law. The amount of substance plated is directly proportional to the quantity of charge. And we can go ahead and calculate the quantity of charge by taking the amperes multiplied by the time in seconds. And once we have the charge, we now can relate the charge to Faraday's constant, which tells us we have 9.65 times 10 to the 4 coulombs of energy for every 1 mole of electron. We can figure out the mole of electron based on the half reaction, which tells us the amount of electrons that are going to be necessary to form 1 mole of the solid here. So for us, for every 1 mole of electron is necessary for Ag plus to gain in order to form 1 mole of solid. And so we have a 1-to-1 relationship between mole of electrons and mole of whatever element we're talking about. For us, that's going to be silver. And then finally, if we want to get down to the mass in grams, we just go from moles to grams. So I went to the periodic table and I got the molar mass of silver, which is 107.8682 grams per mole, and we can use that as a conversion factor. So for us, they're saying what mass of silver can be plated in 67 minutes. So they're starting us off with time. We can go ahead and convert that time to seconds, and we're going to be right here in the overall portion of the understanding of the stoichiometry of Faraday's law. Okay, so if we get our seconds, we can go ahead and figure out our coulomb of charge based on amperes. Then we're in the rest of this overall conversion factor. Let's go ahead and set it up. All right, let's go ahead and start filling this out. So we're starting off with 67 minutes. We know we need to get to seconds, so the first thing we need to do is make a conversion factor. For every 1 minute, you have 60 seconds. So now we have our seconds, okay? Now I went ahead and map this out. So 67 minutes to seconds. Also, I want to talk about the current. We're given 8.70 amperes, and we know that amperes is equal to 1 coulomb per second. So we could write 8.70 coulombs per second. And again, that becomes a conversion factor we can utilize as well. So we're now in seconds. Now the goal is to go from seconds to charge. So we can use this conversion factor to our advantage. For every 1 second, we have 8.70 coulombs of energy. Now again, we're using Faraday's law to help us go from coulombs to moles of electrons. So we're going to take 9.65 times 10 to the 4th coulombs for every mole of electron. And we know based on our overall half reaction that's given, for every mole of electron, we're going to have 1 mole of silver that is formed. Now, in order to go from moles to grams, we use molar mass. And we know that for every 1 mole, we have 107.8682 grams of silver. And so again, our seconds are going to cancel here. Coulombs are going to cancel. Moles of electrons are going to cancel. Moles are going to cancel. We're left with grams, which is what the question wants. We are looking at about 3 significant figures here based on what the answer choices, okay? So when I go ahead and multiply 67 times 8.7 times 107.8682, I get a 1 answer, and then I divide that by 9.65 times 10 to the 4th. I get 39.1 grams as my answer, which is letter C. Number 6 states that non-standard cell potential is equal to standard cell potential minus 0.059 divided by n log of Q, which is the Nernst equation. It also tells us that the concentration of H plus is equal to 1.0 molar initially, and the partial pressure of O2 is equal to 1.0 atmosphere. They give us this overall reaction, which is 4 electrons plus O2 gas plus 4H plus is in equilibrium to form 2H2O liquid. And it gives us the standard cell potential for this overall half reaction. The question says, based on the information above, which statement is correct? So everything from above is going to be based on the Nernst equation. That means if they're asking us any questions about this, they're asking us about how all these different parts relate to one another. So how does this log of Q relate to E? How does E relate to the standard cell potential? How does this entire value relate to the standard cell potential, right? Or the non-standard cell potential, for example, excuse me. So I first, with these type of questions, read the answer choices to help me kind of guide my mind. Letter A, n equals 1 since 1 mole of electrons. So, they're asking about the number of electrons transferred. We can get that straight from a half reaction, right? It's 4 here. And then it says B, the addition of base. So they're asking about the addition of base. That means they might be trying to change something in the Nernst equation here. Letter C, E is independent of the pH of the solution. Kind of extra information, has nothing to do with everything, but it's still something you can add on. And then they actually say dQ is equal to H2O squared divided by O2 squared multiplied by the concentration of H plus. We can verify all this information, but we have to make sure we're relying on this. So for letter A, N is equal to 1. Automatically, we know that's going to be incorrect. I can go ahead and get rid of that because we're showing 4 electrons here. Okay. Now let's look at letter D. Can we verify that this is our actual Q value? Yes, we can. We can get our Q, which is known as our products, concentration of products divided by our reactants. And we know it's also based on partial pressure here as well. Okay. So it could be our concentrations of products, or it could be the partial pressures of them as well. So we have our Q value, which is going to be our products here, which is going to be water. We know that water is going to be 1 for us because it's a pure liquid. It's going to be divided by our O2 concentration multiplied by our H plus concentration raised to a power 4. So automatically I can get rid of letter D. Next, it says that the non-standard cell potential is independent of pH of the solution. Well, we know that that's not true just based off of lab. We know that the non-standard cell potential is equal to 0.0592 volts multiplied by the pH. And so that's the way where we're able to use different electrodes, for example, and relate pH to the non-standard cell potential. So we know that this is incorrect because it is dependent on pH. It's not independent of it. So automatically they say, well, the correct answer is B, just by process of elimination. And that's how some folks will get the answer, and that's great. But what if you did not get that answer that way? Then you need to understand why this is correct still, no matter what. So addition of base should result in an E value, which is the non-standard cell potential value, which is less than 1.23 volts. Let's talk about this. Right now, we are at the standard cell potential, which is 1.23 volts. And we kind of know that we are at a standard state because we do have 1.0 molar, right? And they're telling us that we have that amount initially. We also have 1.0 atmospheres. So you can automatically say, well, at 1.23 volts, we know our non-standard is going to equal to our standard cell potential. So our Q value is going to equal to 1. And if our Q value is equal to 1, if I take the log of 1, then that means this entire value here is equal to 0, which is why we can say that these two are equal to one another. Now they're saying we're going to add base. So if we're adding base, let's go ahead and look at our overall reaction. We have O2, we're going to take out the electrons here. Then we have 4H plus, and that's going to form 2H2O liquid. And they're telling us that they're going to add base. So we're going to add base, let's say OH minus, to the overall solution. Well, when you add base here, it's going to, again, take one of those H pluses and OH minus, and it's going to form water. Okay? And so what's going to happen? You're going to decreasing the H plus concentration. If you're going to be decreasing the H plus concentration, if I look at my Q value, you're like saying that you're going to be decreasing the denominator. If that happens, you're going to be increasing your overall Q value. Okay, so my Q value is now going to increase. Another way to think of it is, okay, I'm actually decreasing my reactant here to form more of an actual product. So you're increasing your product amount, which is also going to, again, increase that number. So now when you're looking at your Nernst equation, you're going to have your non-standard cell potential. You have 1.23 volts, which is what this half cell potential is. And that's going to be minus whatever this new larger number is. So if this number is larger here, let's say it's even 1.24, for example, just a tiny bit larger, then this overall amount for the non-standard cell potential is going to be 0.01, which is going to be less than the 1.23 volt value. So no matter what, as this gets larger, the overall non-standard cell potential is going to get smaller. That is another way you can verify that letter B is the correct answer. For number 7, it states, which is the strongest oxidizing agent? And they give us standard potentials. They don't tell us standard reduction potentials, though. If you see, everything is in oxidation form. And then they give us standard half cell values here. So this means Na is going to lose electrons, and it has a very positive half cell value. So this very positive half cell value means that this sodium is most likely going to give up an electron. And then you can go all the way down to silver, which is going to be silver giving up an electron as well. It's going to be negative 0.80 volts here. And that is going to mean that silver, because it is the smallest value, likes to be in the reverse form, okay? So that means silver actually likes to gain an electron to form a solid versus giving one up. And so it's the opposite of what we normally see if we had standard reduction potentials. So for what is given here, you can say more positive means it's most likely to be what you see as written, exactly as we see as written. And more negative means it's most likely to be reversed. So this one here is negative, so therefore we are most likely to gain an electron here. Now we have to ask ourselves, what is oxidizing agent? Oxidizing agent means that you're going to accept electrons so that another species can be oxidized. So if you are accepting electrons, you are therefore going to be reduced. And the opposite is if you are going to be a reducing agent, then again, you are giving up electrons for another species to gain. So you are going to be oxidized. If they're talking about the strongest oxidizing agent, they're talking about which one of these species have the ability to gain an electron. In other words, which one of these species is going to be in the reverse. So we know it's going to be silver here. Why? Because silver is the only one that has a negative value, meaning it does not like to be exactly as written and likes to actually be Ag plus gaining an electron to form Ag solid. Unlike the rest of them, which have a higher values, as you can see, 0.40 and 2.71, they like to, again, sodium likes to give up an electron, cadmium likes to give up 2 electrons, and hydrogen gas is going to form 2H plus and give up 2 electrons as well. So for this question, it will be letter D. Now, what if you are not giving the actual half cells, right? The actual half reactions. If you were not given the half reaction and say you were only given these values, and they asked you, what's the strongest oxidizing agent? Then you would just focus on the highest, more positive one. So if they did not give us this, and they only gave us values, you would say, okay, the highest, strongest oxidizing agent would be sodium, right? That would make more sense. But you would have to verify again that they're giving you standard half cell potentials for reduction. And since that is something that's more general, you can say that the higher, more positive one will be the stronger oxidizing agent. But for this question, they gave us these standard half cell potentials, but they switched it up by giving us the oxidized half cell reaction, okay, which is very different from how we see it. Just swapped it a little bit for it. All right, let's move on. We have now officially made it to chapter 21 material. So number 8 says the sodium-24, which is used to locate blood clots in the human circulatory system, has a half-life of 15.0 hours. A sample of sodium-24 with an initial mass of 15.5 grams was stored for 45.0 hours. How many grams of sodium-24 are left in the sample after 45.0 hours? Now, the first thing you want to do is turn the page, and I'm turning my page right here, and going to your overall equation sheet. I gathered all the information I could about the first order integrated rate law. So I have the half-life, which is equal to natural log of 2 over k. I also went ahead and got my calculator what natural log of 2 is, which is 0.693. So I can rewrite it as 0.693 divided by k. Also, I rearranged the first order integrated rate law. Natural log of the final condition divided by the initial condition is equal to a negative rate constant multiplied by time. Time is different from half-life, right? They're two different things. And then you also can go further and again relate the fraction of the amount remaining and the amount initial to, of course, k and t. Now what we did here is we took our k value and we solved for it. So we took our half-life and our 0.693 divided by k, and we solved for k, and that's how they got the natural log of 1/2 here, and of course t divided by t of 1/2. Sometimes this t divided by t of 1/2 value is just simply seen as n, so we can rewrite this as, if we take the natural log of both sides, we can rewrite this as the final amount is equal to the initial amount multiplied by 1/2 raised to the power of n. And that n value is going to be your time divided by whatever your half-life is. And this is just a quick way to get any amount that's remaining based on the question that's given. And so for us, let's go ahead and see what we have here. Did they give us an initial amount? Yes, they give us 15.5 grams. So we have that value. We already know we can get 1 divided by 2 in our calculator. Now let's get our n value, which is going to be time divided by our half-life. Do they give us time? Yes, 45 hours. Do they give us half-life? Yes, 15 hours. We have all the components necessary to be able to answer our question. So let's go ahead and fill this out. This is why I'm telling you that the overall formula sheet is very useful for you. All right, so I'm going to take my expression. Amount left is equal to my initial, which is 15.5 grams, multiplied by 1/2 raised to my n value. My n value is going to be my time, which is 45.0 hours, divided by my half-life, which is 15.0 hours. So I get 15.5 grams multiplied by 1/2 raised to the power of 3. I take my 1/2 in my calculator, and then I raise it to the power of 3. I get 0.125. I multiply that 0.125 by 15.5, and I get 1.94 grams as my final answer. And of course, the significant figure should be 3, so I am good. All right, number 9 says identify the missing particle. So first you have to tell yourself what is a particle. Particle is going to be an electron, a proton, or a neutron. Now, how do we write that when we're dealing with this here? For the nuclear chemistry, there's going to be 0 for a negative, 1 for electron, 1 for proton, and 1 0 for neutron. And this is basically showing us the mass and also the overall charge as well. Okay? And then I also want to go further and write the decay mode. So we have alpha decay, beta decay, positron, electron capture, and also gamma as well. So just writing down little details for ourselves to help. Now, the goal of figuring out how to identify a missing particle is making sure you balance. And what are you balancing? You're balancing your atomic numbers and your mass numbers. All right, so for every isotope, you're going to have a mass number, which is going to be your sum of your protons and neutrons. You're also going to have an atomic number, which identifies the overall element, and that's just going to be the number of protons. You can subtract these two to get the number of neutrons. So what we want to do is we want to make sure the atomic number, which is at the top here, the mass number, which is at the top here, and at the atomic numbers at the bottom are going to equal on each side of the overall equation. So I kind of set up both sides of my equations. As you can see here, I put my 3 plus 2, I put my 1 plus 1 at the bottom. So again, I am adding up my mass number here, and I'm adding up my atomic numbers. So 3 plus 2 is going to be 5. And so I have 5 on this side, and I have 2 on this side. That means I should have, again, an equal amount of number on that side. And this is going to help me figure out the mass number of the missing particle. So here's 5. I have 4 here. I have 0 because this is going to be gamma emission that was gamma array that was emitted here. So it's going to be 0. So 4 plus 0 is not going to give me 5. I need to make sure that this has to be 1 in order for me to get 5 on this side. I'm going to do the same thing over here. I have 2. This is 2 plus 0, right? And then so that my x value has to also be 0 in order to keep everything 2. So everything is balanced now. Again, I can just go ahead and say, what is my overall x? My x particle is going to be 1, 0, which then is going to be a neutron and letter B. All right, so number 10 says determine the binding energy. So you have to understand what binding energy is, which is basically the energy necessary to break something or build something, right? So for us, we're talking about the nucleus. What's in the nucleus? Protons and neutrons. And so if we're thinking about that, we're talking about the nuclear force between the protons and neutrons. They build that nuclear force by, of course, bringing together protons and neutrons in fusion, or the ability to break down that nuclear force by, of course, breaking them apart in fission. In other words, you can also say it's the energy associated with taking a heavier nuclei and breaking it down into lighter ones, or like we would in fission, for example, or taking lighter nuclei and building them together to form a heavier one, like we would for fusion. Either way, it's going to cause a great mass change or difference in mass and release loads of energy. And we can actually relate the change in mass and energy by using the equation of energy is equal to mass times the speed of light squared. For our change in mass is, again, going to be that difference in the change in mass once we are, again, putting something together or, of course, breaking it down as far as the nuclei go. This also can be called the mass defect as well. And how do we get that? We take our mass number, which is going to be our protons and neutrons, the total amount, and subtract it by the nucleus itself. And then for C squared, we actually find that it equals to 931 mega electron volts. This value is also given. Let me just also make sure it's given on your thing too. Yes, this whole thing is also given to you. Now the 931 mega electron volts, I'm giving this to you now. That is the connection you can make because we're going from using 1 AMU, which is equal to 931 mega electron volts per C squared, okay? And that's how it's able to get C squared is equal to 931 mega electron volts. All right, and we're using that to solve for the energy. Now let's go ahead and continue on. So they want us to determine that binding energy just by using all this information. They give us the O16 isotope nucleus. They tell us it has a mass of 15.9905 AMU. They say a proton has a mass of 1.00728 AMU. Neutron has a mass of 1.008665 AMU. And 1 AMU is equivalent to 931 mega electron volts of energy. Exactly what I showed you here. All right, let's go ahead and set ourselves up. The first thing you want to do is focus on the oxygen. Now we know it tells us it's O16, so it already gives us the mass number. And we can go ahead and get oxygen from the periodic table to get the number of protons. So I went ahead and got oxygen. It already has our atomic number here. We know that's going to be the number of protons, which is going to be 8. I can take 16, which is the mass given, minus the number of protons to get 8, which is going to be the number of neutrons. So we have 8 protons and 8 neutrons. Now, we want to make sure that we're getting all these values. We already got our C squared value. That's 931 mega electron volts. We're looking for our E value, so we have to solve for our mass defect. And we know that's going to be the mass of our total protons plus neutrons. Sometimes you can simply call this the nucleons, okay, or mass number, minus the actual nucleus, okay? And the nucleus, we already gave, that was already given as well. They gave us that at 15.9905 AMU. So let's go ahead and get our nucleon number or the total protons and neutrons. How do we get the total? Well, we're given 8 protons. We're also given the mass of the protons of 1.00728 AMU. We're also given 8 neutrons and that mass at 1.008665 AMU. All right. Now, what we need to do is add these two values together. So I'm going to add, multiply these first, and then, of course, multiply this one, and then add those two values together. All right, so to get my nucleons or the total protons and neutrons, I'm going to take 8 and multiply by 1.00728. I get 8.05824. Then I'm going to take my number of neutrons, which is going to be 8, and multiply that by the mass of neutrons, which is 1.008665. And I get 8.06932. When I add these two numbers together, I get 16.12756. That is my total mass of nucleons. I'm going to subtract it by the mass of nucleus given, which is 15.9905. When I subtract these two numbers, I get a mass defect, or delta M, of 0.13706. So now I have my delta M value, I have my C value. I can go ahead and calculate my delta E value, or my binding energy of O16 nucleus. All right, so I took my delta E is equal to 0.13706 multiplied by 931 mega electron volts. And I get 128 mega electron volts as my final answer. And this means this is the amount of energy between the protons and neutrons in O16 nucleus. All right, so for number 11, it says which nuclear equation is properly balanced. They give us letters A through D. And so, of course, we must make sure that we go through all of these letters to complete the question. Now, if they're talking about properly balanced, that means they just want us to focus on the atomic number and mass number. We must make sure that the atomic number at the top and the mass numbers at the bottom are all going to be balanced. A lot of times they will not give you the mass numbers, or sorry, the atomic number here. And that's because they simply just use the element symbol for recognition. So you can say, okay, well, look at this one here. This is helium. They didn't put a 2 here, but I always go ahead and say, let me go ahead and write all my 2's for helium. I know it's helium, but I have to make sure that I am getting everything balanced. Do the same thing for hydrogen. I know there should be a 1 here for all of my hydrogens. So I go through and just make sure that all of them have a 1. So when I'm balancing my atomic number, everything's good. Same thing with my beryllium here. That's going to be 4. My nitrogen is going to be 7. Magnesium is going to be 12. My nitrogen here is going to be 7 again. Oxygen is 8. We just saw that one. Silicon is 14. Oxygen is 8 again. And carbon is 6. So now we have all of our atomic numbers. Everything looks good. So what am I doing for letters A through D? All I'm doing is basically putting a little arrow, and I'm going to count up my atomic number and my mass number. So I'm going to put my mass numbers here and my atomic number at the bottom. And if they match, then they are properly balanced. If they don't match, then they are not properly balanced. And you just go one by one to figure out which one is the correct one. All right, let's focus on mass number for letter A. So it's 9 plus 4. That's going to be 13 at the top here. And then 4 plus 2 is 16 at the bottom. It should match 13 and 6 over here. So we have 13 at the top, that's matching, but we have 7 at the bottom. So letter A is out. Let's go to letter D, just going back and forth. We have 14 plus 0, so that's going to be 14 at the top. 7 minus 1, that is going to be 6 at the bottom. This is going to be 14 and 8. They don't match. Letter D is out. Now we're only down to B and C. So letter C, we are going to have 24 plus 4. So that's 28 here at the top, and we're going to have 12 plus 2. That is 14 at the bottom. Now over here, we're going to have 28 at the top, so everything's good, and we only have 15 at the bottom. So again, this is not fully balanced. That means process of elimination, letter B is correct. Let's go ahead and verify letter B. So we have 14 plus 4, which is 18 at the top, 7 plus 2, which is 9 at the bottom. Over here, we have 17 plus 1, which is 18 at the top, and we have 8 plus 1, which is 9 at the bottom. This is balanced, so we are correct. All right, number 12 says uranium-234, so we know it's an isotope, undergoes spontaneous radioactive decay. So it breaks down spontaneously to give an alpha particle in a new nucleus X, okay? So it shows that here. We have uranium-234, and it's going to break down to give us an alpha particle in X. So first we have to figure out what this all means. What does it mean when it goes spontaneous radioactive decay? That means we're going to have a nucleus that's going to break down and decay to a daughter nucleus and emit some form of radiation. So one mode of decay for radiation will be alpha, beta, gamma, positron, or beta plus, and then EC for electron capture. Okay, folks? This question is focusing on an alpha particle. That means you're going to have your nucleus here, and it's going to decay to its daughter nuclei, okay, plus an alpha particle, which is going to be the helium that we see here. So usually going to be your helium, which is a mass of 4, and then it's going to have an atomic number of 2. Sometimes you'll see it written as just alpha. Sometimes you'll see 4,2 alpha, 4,2 helium 2 plus, like I have it written here, or just 4,2 helium. So there's more than one way to look at it or see it. So don't be alarmed if you see it more than one way written out. Okay, folks? So for this decay, again, I have my daughter nuclei, which again, for this overall, we don't know what the daughter nuclei is, but I do know I have an alpha particle. So I'm going to go ahead and write my 2 here for the atomic number for this. And for uranium, I'm going to go ahead and write my 92. I'm getting these straight from the periodic table, right? Now, this question is all about the alpha decay or the alpha particle. Remember, don't just focus on the alpha particle. Focus on all modes of decay, folks. So remember, you will definitely want to focus on beta, okay? And of course, positron, electron capture, and gamma as well. All right, so that's all the information. Let's go ahead and figure out what X is. How do we do this? We go ahead and balance like we've been doing everything else. What are we balancing? We're going to be balancing out that atomic number and that mass number there, okay? So when we're looking at this one over here, we have 234 because we have the uranium, and then we have 92 for the atomic number. On this side, we're going to have 4 and 2. We already know that. So to figure out our X value, we just got to take our 234 and subtract it by 4. That's going to be 230. And we're going to take our 92 and subtract it by 2, and that's going to leave 90. And so automatically you see your answer choices. Letter C is automatically out, and letter D because they have the incorrect mass number. So we're down to A and B. And as you can see, they both have 90 here. And so we have to distinguish them based on the elements. So you go to the periodic table and you find the number 90. When you go to the number 90 on the periodic table, which is going to be the atomic number, which gives the identity of the actual element, you'll see thorium is going to be the identity of the element, so it's going to be letter B. All right, folks, that is exam number 4. So you want to, or practice exam number 4, you want to make sure that you are utilizing the overall, formula sheet that is given to you because it has so many goodies on there to help you out through a lot of these questions. Okay, folks? And then finally, you also want to make sure you're doing practice outside of exactly what you see on the practice exam. So for example, with this question, just talking about alpha particle, what if gave you a beta particle for instead? Will you be able to identify that, for example, and be able to continue the question? Little things like that will be able to help you along. Again, if you are over the homework problems, you always can go to the textbook exercises to get more practice. Let me know if you have questions, folks. Sorry, I am like tongue-tied. I apologize. Y'all have a good one. See you later.